Thanks, Peter. So I'm so happy to be here with this amazing lineup of speakers presenting the recent advances that we have seen at the intersection of deep learning and combinatorial optimization. In the last 3 to 4 years, this field has really grown. It's an exciting research area with a lot of potential, where we have seen attempts at replacing combinatorial optimization algorithms with purely deep learning approaches to integrating machine learning into discrete optimization algorithms, an area in which I have done a bit of work, mostly in collaboration with my former PhD student, Elias Khalil, who is now an assistant professor at the University of Toronto, where one can basically take existing combinatorial algorithms and try to make them smarter by integrating ML-guided components. And we have done in this area things like train greedy algorithms for graph optimization algorithms with reinforcement learning. Lee Song talked about this work earlier in the workshop, or using machine learning to guide branch and bound for mixed integer programming, both for branching and primal heuristic selection. And we saw some follow-up improvements presented also in the workshop earlier this week. But today, I want to talk a little bit more about a different direction of integration, where we are thinking about how to infuse machine learning with knowledge of the constrained decision-making, combinatorial decision-making that comes after it. So we want to incorporate knowledge about the downstream combinatorics into the training loop. And the work I'll talk about today is mostly in collaboration with Brian Wilder while he was at the University of Southern California. Brian now is at Harvard and is actually on the job market. So in many real-world applications, we have a familiar pipeline where we have some observed data and we use that data to learn models in order to make predictions. And with those predictions, then we make resource allocation and other decisions for future steps. And most of the time, the way that this in the real world, these settings are addressed is really to first start with building a machine learning model that is as accurate as possible. So maximize accuracy. And once we are done with that, hand that over to our optimization team, which comes up with a good model and good algorithm, be it mixed integer programming, greedy, etc., which is then trying to maximize decision quality using the ML parameters as inputs. And this two-stage approach leaves really a lot on the table. So imagine the following setup where we have historic data about travel times on different road segments, and we can use data such as weather, time of day, the network, and other things to build a predictive model of travel times, and then use those travel times for a specific company which has to route its trucks around the city. Now, this knowledge that these predicted travel times will be used for a specific application, not only for a specific application, but actually by a specific client, which has a specific distribution of decision-making needs. It's a huge knowledge that we can exploit. In particular, we might really need to make sure that only specific types of roads or specific part of the network is very well estimated, and we can use that to shape the accuracy of our ML model. So by focusing the predictions only on maximizing accuracy by comparing predicted delays with actual delays, we are really trying to minimize the error across all the data that we have without incorporating this downstream task for doing routing for a specific company. And the problem with that is that maximizing accuracy doesn't always translate into maximizing decision quality. Obviously, if we had enough data and we could train a perfect model, perfectly accurate model, then we are all good. But in most real applications, something that Zico Kotar also highlighted in his talk earlier today, we don't have that. And so what we really want is, at the end of the day, to create a pipeline that produces the best outcomes possible, and those are really measured in terms of decision quality. So we have here a situation in most real world settings where all models are wrong, but some models are useful. So how do we make our models more useful? A two-stage approach doesn't really align perfectly with our end goal. So let's try to do something better than this. So the key idea is that we want to automatically shape the machine learning model's loss by incorporating combinatorial optimization problems into the training loop. Okay, and so here in my example with the routing from earlier, what that would mean is that I would use the data to run it through my predictive model, predict delays, use those delays for the making decisions with specific, again, distribution of optimization settings in which I would use those predictions, and then compute the quality of the shortest path that I get with respect to the ground truth and update my model to improve the chosen path with respect to the actual delays. So we call this idea, this setup of really thinking about this final combinatorial decision-making as the driving force, decision-focused learning. And so there's been a line of work that is focusing or thinking along these lines. In particular, the work by Dante, Amos, and Coulter from 2017 also basically talked about this setup, calling it task-oriented learning in the context of convex optimization. Here we are going one step further, really wanting to set this up specifically for combinatorial optimization problems. And in fact, some of those thoughts about taking the decision-making closer to the predictive model training has come up much earlier, even in early work by Benjo in 97. So the first part of the talk is going to be really focusing on our paper led by Brian Wilder on melding the data decisions pipeline from IIII 2019. So we have a decision problem with discrete decision variables and some unknown parameters, in our case, the coefficients in the objective function that we'll be estimating with our ML model. And so the key idea is to try to create a framework where we can take the derivative of the decision objective with respect to the machine learning model weights, which basically account for our objective coefficients we are using, and train via gradient descent. So essentially create a differentiable optimization layer such that we can incorporate into a deep learning architecture. And again, a similar approach was presented for convex optimization in Dante et al. So just to highlight the steps that we need to take care of, essentially in the forward pass, we have our data, we run through our predictive models, get our coefficients, run this through our optimization algorithm, and then get the proposed solution and evaluate that solution with respect to the ground truth, which during training we obviously have. And then in the backward pass, we need to figure out a way of differentiating the objective value of our decisions with respect to the decisions that we made, and then differentiate these decisions with respect to the predictions, the coefficients that were fed by the ML model, and then finally those predictions as a function of the weights, something we already know how to do. Okay, so one thing to understand here is that during training, we need both the historical data in terms of the observables that we're going to use for our predictive models to estimate the coefficients in our objective, as well as historic data on the kind of optimization problems that we then need to solve with those coefficients, right? So here we have two kind of sets of data. You can think of this as, let's say, historic data about Amazon's distribution, right? You can have both data in terms of that can estimate supply and demand, and then you also have the daily data on what actual optimization problems they needed to solve. Okay, so the big challenge here is that we want to actually solve discrete optimization problems. So we need to find a way to create a differentiable version of that. And so we're going to use a familiar approach similar to the SATNet approach that, again, Zico talked about earlier this morning, where we're going to relax to a continuous problem, differentiate, and then round if needed. So, the big challenge here really is how to compute the derivative of the decisions that we make with respect to the predictions that the ML model outputs. And the key idea that we leverage here from prior work is to use the fact that locally optimum continuous solutions must satisfy the KKT conditions, and then basically use those in order to differentiate through a system of linear equations that results from that. Okay. So let's jump into combinatorics. So we have seen this done for quadratic programs and for stochastic optimization prior to our work in 2019, but we really wanted to extend this to solve combinatorial problems. And the first class of combinatorial problems we looked at was a simple one, is combinatorial problems that can actually be encoded exactly with linear programs, or even combinatorial problems that have very, very strong LP relaxations. Okay. The problem here is that because we basically, with small changes to our parameter estimates from the machine learning model, which basically control our objective, a vector here presented by theta, with small changes in these estimates, we can actually flip-flop between different possible optimum solutions under those estimates. And that's really bad news for us. And so the standard quadratic programming solution would not work. So the standard differentiation just through this KKT from the LP would not work. So we add a regularizer in order to get smoothness again. So with this regularizer that you can see here, we essentially can then have a probably differentiable encoding that is also close to the original LP. Okay, great. So let's see whether this actually works in practice. So in the paper, we actually present results also for how to solve submodular maximization using the multilinear extension. And here for briefness, I would skip these details. So we evaluated our approach with respect to 3 different application settings, budget allocation, bipartite matching, and a recommendation problem. And we evaluated our decision-focused approach with 2 different architectures of the neural network for the machine learning model versus the 2-stage approach, where we separately train the neural network just with maximizing accuracy and then solve the corresponding optimization model with these parameters and evaluate it with the ground truth. So you can see in these results that decision-focused learning can actually consistently provide improvements over the 2-stage approach, providing 15 to 70% improvements over the 2-stage approach. And this is great, but one of my pet peeves with this was that I really wanted us to find a way to make this work for the general case, for mixed integer programs, a family that can encode so many real world NP-hard problems and take care of site constraints, etc., things that would be really, really hard if we had to stick to purely LP amenable problems or submodular maximization. Okay, I'm jumping ahead of myself. I guess before going to mixed integer programming, I wanted to mention that in a follow-up work, we actually use the results of our IIII paper for a very important application, trying to improve tuberculosis treatment in India. This was a collaboration with an NGO called Everwell. And we actually use historic data from their operation in order to build a model. Here again, the goal was to have this pipeline where, based on historic data, we would predict whether patients will miss a daily dose or not. And with those predictions, we'll allocate the very limited resources that they have, in particular health workers, to visit the most at-risk patients. Right. So our optimization problem was can be modeled as a LP. And so in this follow-up work, we showed that our decision-focused approach can really outperform the two-stage approach, which was kind of like the standard practice, with about up to 15% improvement in successful interventions. So definitely there is a lot of promise in this. Okay, so now moving to mixed integer programming. So how can we get these approaches to work for this much more general family? We already know how to differentiate through the LP from our prior work. And so in fact, it turned out that the leap is not that big. It was right there under our noses all along. Well, we know how to solve mixed integer programs using cutting planes, which results actually in a final LP solution, which basically has these added cuts such that when you solve this augmented LP, the solution of that continuous relaxation is in fact integer feasible. Okay, and therefore optimum. So then what we can do is essentially integrate this cutting planes algorithm into our training procedure. So we have our inputs, our predictive models, estimate the objective coefficients, plug this into our MIP problem, again with historical data on the remaining parts of the problems like constraints, run this through the cutting plane algorithm, get a very large LP, which results in the optimum integer feasible solution, and then in the backward pass differentiate through that to basically improve the weights on our neural network. Cutting plane algorithms are often slower than branch and bound. The nice thing is that at test time, we don't need to use cutting planes. We can use our improved ML algorithm, which predicts coefficients that optimize for our decision loss, and use those predictions to formulate a MIP and solve this MIP with any algorithm that we like, such as branch and bound, because we have basically been solving the training instances to optimality. So this work was presented in a IIII 2020 paper. It's called MIP as a layer, and was led by my PhD student Aaron Ferber in collaboration with Brian Wilder and Milin Tambe. So let's see whether this again works in practice. We evaluated this approach on 3 different domains. The main domain was portfolio optimization, where we need to predict a monthly rate of returns for each asset. Based on this information, we want to optimize our portfolio with a lot of side constraints like limiting risk, sector exposure, transactions, etc. And this results in a mixed integer programming problem. And we have very nice data sets from SP500 from the USA and DAX from Germany. In addition to that, we also evaluated our approach to on diverse bipartite matching, where we want to predict the match success probability, essentially the edge probability. And we want to then, based on that, optimize the total number of successful matches. But here we incorporated side constraints, which essentially meant that an LP approach was no longer exact. And these are things that can often happen in the real world, where we might have lower bounds or upper bounds of different types of entities that need to be matched. And finally, the last application was energy production knapsack, where we can need to predict energy prices and optimize total revenue in our allocation. So here are the results for these 3 domains. And what you can see is that MIPAL gives 2 times improvement in the monthly returns on SP500 and 8 times improvement on the DAX dataset for the portfolio optimization over the 2-stage approach. An important thing to note also that for these problems, the LP relaxation actually doesn't work very well. So if we had just taken our approach from IIII 2019 and used essentially the root LP as our gradient inducing information, we would actually not really get the improvements that we see with directly incorporating explicitly the mixed integer program.
Hey, Bistra, just to let you know, there's 5 minutes left.
Excellent, thanks. So for the matching problems, we see about 40% improvement, and for the knapsack, about 1.2% improvements. Here, we also in the paper evaluate a bunch of variants of this MIPAZA layer, where we evaluated early stopping, warm start, etc. And you can see the details in the paper. So we trained these algorithms based on a distribution, both of the data and of the actual combinatorial instances that we need to solve. But can we actually generalize? So we, in addition to perfectly in distribution testing, we also looked at transfer learning. So we took the SP500, we took only 30 assets out of those. We trained on them with a data set that we call 30ASP. And then we applied that model to a brand new unseen set of assets, SP30B, which has the same number of assets, but they're different, right? And so you can see that actually we are able to transfer some of this learned bias to a new set of instances. And then we go one step further, we actually transfer this model to DAX, which is in a totally different, in a sense, market. And finally, we evaluate generalization in terms of size. So we train on portfolio optimization problems over 30 assets, but then test on solving test time instances with 50, 100, 200, and 500 instances based on the ML model that was trained with 30. And again, we see that we can actually still significantly improve over a two-stage approach with this. So decision-focused learning, it basically focuses on the idea that there's no need to silo out machine learning versus optimization task, and that when data is scarce, we really want to make the predictions accurate where it matters most. And how do we know where it matters most? Well, it's by basically incorporating the information about the prescriptive downstream task into the training loop. So there has been several related frameworks to this idea, in particular, empirical decision model learning by Lombardi, Milano, and Bartolini, predict and optimize framework and its variants, and recently black box differentiation of combinatorial solvers from Max Planck. And so I believe I have a couple of minutes, and I just wanted to very quickly mention another line of work that we have recently done, which is basically realizing that often we still come up with, against scalability issues, doing differentiable optimization based on KKT condition, it results in a cubic runtime, and so therefore often doesn't scale. So another approach, an alternative approach to doing that, to basically relaxing and differentiating, is to learn a representation that maps the original problem to a simpler proxy problem. And we show how this can be done for a class of graph problems in our paper in Europe's 2019, again, led by Brian Wilder, which is called End-to-End Learning and Optimization on Graphs. So here, often we have this setting where we would use machine learning model to do link prediction, and then use those predicted graphs in downstream optimization, things like partitioning, facility location, influence maximization, etc. So these types of problems, partitioning and selecting subset of k-nodes like facility location, actually can be replaced by a proxy using clustering, right? So partitioning corresponds to well-connected subgroups. Facility location can be thought of putting one facility in each community. So if we replace these combinatorial problems with this proxy, which is basically clustering, can we incorporate then our knowledge that these downstream graph optimization problems will happen by incorporating our proxy, the clustering, as a layer into the training loop? And that's exactly what we did with ClusterNet, where we have a graph convolutional network which provides node embeddings based on which we perform k-means clustering. And based on the clusters estimated by this proxy, we solve the combinatorial problem by allocating one facility in each community or taking those as our partition groups. The challenge here was, again, how do we create a differentiable version of k-means? And in the interest of time, I will basically just get to the gist of it, where we get the solution of the k-means algorithm, but then use it by unrolling only one update and propagating gradients through that. And so in empirical results, we can see that for community detection and facility location, this ClusterNet approach, where we have this proxy of our graph optimization problem directly into the training loop, creates a lot of improvements over both the two-stage approach and an end-to-end approach, where we just basically try to learn directly to solve the problem with a neural network. And similarly, in facility location, where we are minimizing the objective, we again see improvements. So I will stop here and just get to the takeaways, where decoupled approaches like the two-stage or a pure end-to-end methods, where we just throw away all our algorithmic knowledge about how to solve NP-hard problems, miss out on useful structure. And so really, we can make good decisions by closely integrating learning with the discrete optimization that needs to happen. And so that can be done either by directly creating differentiable optimization proxies or using simple optimization primitives like clustering. Thank you for your attention.